Okay, so here's the solution for the free response question from 2012, number 4. And what I like about this question is it's got kind of a mix of A, B, and BC material. It's also actually, when you step back from it, kind of cool what they're asking you to do. They're asking you to use 4 different estimation methods to find the value of 1.4 on this function. And so they're not actually telling you what the function is. You're never going to know what the function is. You do know what f of 1 is on the function. They give you that value to be 15. They then give you this table of information of the x values and the associated slopes. And they give you some other information, then give you 4 different prompts, A, B, C, and D. A, B, C, and D are all different ways of estimating things. And it's when you step back from the problem, I think it's kind of cool to acknowledge that that's what it is you're doing. But it's also, I think, a really good representation of 4 different distinct methods and how they're related to each other. First 2 being A-B topics, second 2 being B-C topics. So if we start with question A, or part A, they're asking us to write an equation for a tangent line at x equals 1 and then use that tangent line to approximate f of 1.4. So for a tangent line, let's see what we know about this thing. We know that f of 1 is 15. And then we know the second derivative at 1 is 20, which I think will come into play later, but we're not going to need that piece of information to do the equation for a tangent line. So the equation for a tangent line, just any tangent line, of course, is just a linear function. So we're going to get a, what would that be, y minus y1 equals m times x minus x1. And then we need to fill in the pieces we know, and we need to find some pieces that we otherwise don't know. The piece we know, of course, is the 115. So we know that y is 15, and we know that x is 1. So we can plug in our point 1 comma 15. We can then figure out what slope would be at that point of tangency, because again, we know what this thing is at 1. We have information only at one spot, and the slope at that point of tangency is an 8. So I'll put an 8 in for my slope, and that is the tangent line equation. Now we can redo that in terms of y equals mx plus b, but we don't have to. This is going to get us a point. We then use that to approximate f of 1.4. So f of 1.4, squiggly lines means approximate. Let's see, that's going to be our y value in this thing. So what would that be? That would be y minus 15, and then we're going to just need to plug in a 1.4 in for x. And again, you can do y equals mx plus b on this. You don't have to. It's your choice. We can just leave it the way we have it. So 8 times 0.4 would be a 3.2. We're going to add a 15 over, and our answer would be 18.2 as our estimate. Let's see, 8 times 0.4, yeah, 3.2. So we get 18.2 as an estimate. That's using a tangent line approximation. So we're going to get a point for setting up our tangent line itself, and then a point for using it to generate the 18.2 value. Second piece is asking us to use a midpoint Riemann sum with 2 subintervals of equal lengths to approximate the integral value from 1 to 1.4 of the f prime, and then use that approximation to estimate the value of 1.4. Show the computations that lead to your answer. So to estimate an integrals value from 1 to 1.4 of a derivative, well, let's see, if we use Riemann sum, and we need to use 2 subintervals. So what we need to do is look at this data up here and split it into 2 chunks. Well, the first chunk would go from 1 to 1.2, and if we're using a midpoint approximation, is that correct? So we're using a midpoint Riemann sum, that's right here. That means we're going to use the thing that's in the middle of each interval. So the middle of this interval is the height of 10. So that's my height of 10. So I've got a width of 0.2 from 1 to 1.2 and a height of 10. And I'm then going to add that to my second subinterval, which is going to run from 1.2 over to 1.4, so that's also going to have a width of 0.2, and it's going to have a midpoint value, a midpoint height of 13. So again, I'm using this to do an estimate for the integral. We don't actually know what the function is, so there's nothing more I can do than do an estimate. 0.2 times 10 is 2. 0.2 times 13 would be 2.6. And when I add those two things together, I'm going to get a 4.6. Right, and now I need to use that to find the value of f of 1.4. So if I'm using that to find the value of f of 1.4, I've now got to figure out what the heck to do with this thing. So thinking about what to even do with this thing, we're going to take that integral value. That's the amount we're adding to f of 1. So if we take f of 1 and we add the integral from 1 to 1.4 of the derivative, the integral of a derivative just is the function, so that's giving me the additional functional value from 1 to 1.4. So f of 1, I know that's to be 15, and then I'm going to add this amount, this 4.6 on, and that's going to give me an estimate value of 19.6. These are the computations that would lead to the answer. You know, certainly you could show steps a little bit differently. You're going to generate a point for coming up with the estimate. You're going to get a point for showing that you understand that you're accessing the fundamental theorem of calculus. And then you're going to get a point for the solution. And I'm getting a little sloppy. You know, one thing that I kind of froze there on, I should be using those little approximation squigglies. I really don't think that would be a problem on this one, as to the fact that they're literally stating that they want you to find an approximation, but just good to have in there, I think, in general. And that actually was part B, wasn't it? Not part A. So there's a set of 3 points, previous set of 2, another method of estimation, 2 ways of using calculus to get an estimate for the function. Part C represents a BC method. So that's using Euler's method starting at 1 with 2 steps of equal size to approximate f of 1.4. So if we're going to use 2 steps to get from 1 to 1.4, and we're going to use Euler's method, if we're going from 1 to 1.4 and we're using 2 steps, what we want to do is start at the y value for 1, and then I want to move forward however much slope I know exists at that function, or at that spot on the function. And so going back up to the table, I know at 1 I've got a slope of 8. So I'm going to use that initial f prime being 8. And I'm going to say, okay, to get to 1.2, because they've asked for a step size of 0.2, I'm going to take my 15 and I'm going to add 8, but not a full step of 1 for slope. My step amount is just 0.2. So I'm only adding 0.2 of run, not a full 1 of run. And then 8 is our rise over our run. So that's giving us what our amount that we need to add on to the 15 would be. And then I'm going to take 15 plus 1.6, and that's going to get me to a 16.6. That's my value at 1.2. Now to get to 1.4, I'm going to do that same 16.6, and I'm going to add whatever the slope amount is at 1.2. Just like here we use the slope at 1, here we're going to use the slope at 1.2. So I'm going to go back up here. The slope at 1.2 on this table is 12. So I'm going to go back to this expression and say, okay, let's take our slope at 12. And again, I'm only going to run with that for 0.2, not a full 1. So I'm not going to use the full 12. I'm just going to use 0.2, the step of it. And that is going to be, what, 16.6 plus 2.4, which would get me to a value of 19 as my estimate. So correctly using Euler's method is showing the first step is going to get you a point, and then showing the second step with the correct solution is going to generate a point. And you're 19 being the answer on that one. So you're taking 2 steps using Euler, each step being 0.2, and you can see we're getting these estimates. This one's a 19, the previous estimate was 19.6, and the first estimate we generated was 18.2. 3 different ways to estimate the function's value. The fourth way, part D, they're asking us to write a second-degree Taylor polynomial centered around x equals 1, and then use that polynomial to approximate f of 1.4. Okay, so a second-degree Taylor. Well, let's see. in general, what a Taylor looks like is a set of values where we've got, what would that be? It would be x minus 1 because we're centered around 1. And then we've got our n factorial. On the bottom, we've got our derivative, or nth derivative. And then we're raising this to the n power, and we're going from n equals 0 to infinity. We don't need that generic term, but for me it just helps to write it. So for our first term, and we're looking at the center actually, so this isn't x, this is a 1, because we're looking for the value of the derivative at 1. So we need to plug in the derivative's value, the 0th derivative's value. Well, the 0th derivative value, that's a tough one to say. The 0th derivative value, that's just the 0th derivative is the function. So I'm going to take the function's value, which we know to be 15. X minus 1 to the 0, that's just 1 divided by 0 factorial is 1. So my first term is 15 plus the first derivative. Well, the first derivative we've used a couple of times. They said the first derivative at 1 was worth 8. So there's my 8 times x minus 1 to the first power. I'll just leave it as x minus 1 divided by 1 factorial, which again we typically wouldn't write in. And then I'm going to do one more, so I need to do the second derivative's value at 1. And I think that was that piece of information I never used yet. Yep, this is right there. The second derivative's value at 1 is stated as 20. And up till now, I haven't needed that piece of information. So they just provided that for this particular step. So that would be 20 times x minus 1 squared, all over 2 factorial. I'll write that as 2 factorial, but of course that's just 2. So then we've got this as our Taylor polynomial of degree 2. Did they say degree 2? Second degree Taylor polynomial. So here's my second degree Taylor polynomial. And what I then want to do with that is use it as an estimate. So now what I'm going to say is, okay, let's plug in 1.4. Well, it's going to be 15 plus 8 times 0.4, because if I take 1.4 and subtract 1 from it, I get 0.4. And then I'm going to take 20 divided by 2. Well, 20 divided by 2 is 10. It's just a clever way to write 10. And then I've got that 0.4, I'm going to square it. And this is number 4, so this is by hand. You're not using a calculator on this. And I would have 15 plus 3.2 plus 10 times, what would that be? 0.4 times 0.4. That's 0.16 when I multiply 0.4 times 0.4. And then I've got 15 plus 3.2 plus 1.6. And when I add those together, I'm going to have 18, 19, and a 0.8. And there's my last approximation. That's a point, and then your Taylor polynomial is a point on this one, which brings us up to 9 points total. And again, 19.8, that's an estimate. Compare it back to the 19 we got on part C, to the 19.6 we got on part B, and to the 18.2 we got on part A. They're all different ways to use calculus to come up with an estimate for this function at 1.4. I think it's a really nice problem, and it represents a way in which the AP can check off multiple things with one free response. So I think it's a very good one for us to practice this particular year.